Okay, so I think we can get started. So hello everyone and welcome to the Hebrew University CS Colloquium. Today we are pleased to have Eylon Yogev with us. Eylon is a postdoc at Tel Aviv University and Boston University. Prior to that, he was a research fellow with the Simons Institute and a postdoc at the Technion. And he did his graduate studies at the Weizmann Institute and his BSc at Tel Aviv University. And today he's going to tell us about adversarially robust streaming algorithms. So without further ado, Eylon, the stage is yours.
Okay, hi everyone, thank you. Thank you first for inviting me. Please feel free to open your camera if you want. And please, if you have any question at all, just feel free to unmute yourself and ask. And please be rude, you don't have to wait for me to finish a sentence, just ask any question you have. It's more fun when it's an interactive dialogue. So I want to tell you about adversarially robust streaming algorithms, and more generally about how I see the connection between an adversary and an algorithm. So here, this is how algorithms used to work. Okay, we have a single machine that is performing the processing. It has some data set that sits locally on this machine. Here it's trying to run my favorite algorithm, Dijkstra, and it gives us some output. This is at least how naively we think and model a standard algorithm. This is not exactly how algorithms run today. Okay, today you can say we live in the big data era. We have a complex online environment, and I want to emphasize a few issues here. So first, we have huge amounts of data, okay, and also they're scattered all over the world, okay? It's not sit in one single position. We have many different computational devices that jointly communicate in order to compute some global task. And also we have data that is being generated constantly, okay, and being generated constantly at a very fast pace. And this is very hard and very difficult for industries to store and index, and for research to analyze and make some use of it. So how do we deal with this? Okay, what we do is we define new computational models. Okay, and I want to give a few examples of this. So one computational model is we use the cloud. Even though in my pocket I have like a $50 cell phone, I can still do very sophisticated queries. I upload them to the cloud. These are companies that manage to get these large server farms. They perform the computation for me and they give me back the answer. Okay, so this is really a huge success story, and this is really changing how we think of an algorithm. Another example is distributed algorithms. So here I don't have one computational device, I actually have many computational devices. Each computational device has some local input that he sees, okay? I don't have any machine that even has the entire input. And now we have to perform some protocol and they need to communicate in order to compute some global function of the data. And the last example is streaming algorithms. And this is gonna be the main topic of this talk. So in streaming algorithms, we have this very fast stream of data that is continuously coming, and we have this algorithm that sits and tries very quickly to perform some analysis, some statistics about the stream of data. And all of these are huge success stories with communities behind them and a lot of work. And this is the part where I put on my cryptographic hat. And my main claim is that all of these models are prone to adversarial behaviors. Okay, so there is some danger with these models that we need to take care of, and I want to give a few examples. So let's start with the cloud. So suppose I want to train this neural net on some large data set. Okay, so I send it to the cloud and I tell the cloud, you know, run for a week, okay, on this large data set of images and give me back the weights of my neural net. The cloud has a lot of incentive not to do this computation, but maybe only to train for a few days and send me back the results, okay? And the point is that really I would have no way to distinguish whether the cloud performed the computation as intended. This is something that is of interest of me and that I worked on, and I want to somehow just give a quick sample of one recent work. So here in this work, we consider the cloud to be a social network. Okay, so you can think of Facebook or Twitter or any other graph that can be modeled as a social network. And what we do in this work, we show that there's a way that social networks, okay, so think of a Twitter or Facebook, can prove various measures, okay, for example, the number of active users in their network. So Facebook claims that they have 1 billion active users, and this is some claim that is hard to check, okay, we don't have full access to this network. And at the heart of the result is, I think, a really nice connection between the methods of proof and interactive proofs and random walks on graphs. Okay, so really a graph theoretic algorithmic perspective. And we hope that this might lead to new regulations on social graphs. So this was the cloud, and we saw just a small example of the adversarial point of view of a cloud. Let's go to distributed algorithms. There's many places where we use distributed algorithms, social network, data centers, Bitcoin networks, and so on. And we have a lot of protocols to really compute things efficiently. So we have many different participants. They all have some private data. And then we have some algorithm telling them, okay, you send this message here, you send this message here. And after a few rounds, they can compute some global function of the data. And this is great, but suddenly somebody is telling me, you know, you have to take the data that sits on your computer and send it to some other people on the network, okay? And I might not be willing to do that, okay? So here the adversary comes with respect to privacy concerns, okay? So I'm willing to participate in a protocol to compute the average salary of people in the Hebrew University, but I don't want anybody to learn my personal salary, okay? So this is the privacy point of view of distributed algorithms. Now, if you know a bit about crypto, you could say that this problem is solved, okay? We have what's called MPC. This is multi-party computation. Okay, we have protocols, we have ways to compute functions where nothing is learned except the final output. The problem with these things is that these protocols really are aimed for security and less for efficiency. Okay, they weren't designed to respect the specific distributed model that you're thinking of. And there's many ways to define the distributed model. So really the main challenge is to take a secure algorithm, okay, and to take an efficient algorithm that isn't secure, and the secure algorithm isn't efficient, and to combine them to get something that is as efficient as the efficient algorithm and as secure as the secure algorithm. And this is something we did in a line of work. So really the main results are ways to develop secure distributed algorithms, okay? And at the heart of these results, so really the security requirements very fastly translate to combinatorial properties on graphs, and specifically what we call a new cycle theorem. And if you're interested, you're welcome to ask me after the talk. And these cycle theorems actually had very surprising implications. So they give faster graph algorithms, even regardless to secure computation. And there's many open problems in this area, if you're interested to work on it. Okay. So this was just a taste about distributed algorithms. And the main topic of this talk is going to be streaming algorithms. So here, it's very unclear where is the adversary. Okay, we have a streaming algorithm, we have data coming, we have some machine that is doing some computation, and it's very unclear where the adversary is. And I'm gonna dive deep into this and tell you exactly where it is. Let me just quickly say it's in how the data is generated, and I'm gonna explain exactly. I just wanna take one step back before we dive into this. Okay, so this is going to be streaming algorithms, and just taking one step out. So this is one slide on my research topics. So this is me. This is my cryptographic perspective on algorithms, and this is a big world of algorithms. We're going to see streaming. We talk slightly about distributed and cloud. There's very similar examples and things that I worked on data structure and sublinear algorithms. Maybe the most famous and trendy topic is machine learning, where we know about adversarial examples in machine learning, which is a huge topic now. Okay, so this is just one slide about me. Okay, so streaming algorithms. So let me start by defining slightly more precisely what a streaming algorithm is. Okay, so this model of algorithms come in place where we have larger amounts of data, and also data that comes in a real-time fashion, in an online manner. Okay, this could be internet traffic, this could be financial transactions, could be network sensors, and so on. And what we want here, we want a one-pass, low-memory algorithm. Okay, so the algorithm sees the data is x1, x2, x3, and so on. This is the stream of elements. Okay, the streaming algorithm gets these elements one at a time. Okay, and it's one pass, it cannot go back. Okay, after it saw x1, x2, now it's observing x3, it cannot go back to x1. Okay, except if it's stored x1 explicitly in memory. Okay, so it has some memory, and if it's stored x1, then of course it can go back and check x1, but really the goal is to have a low memory algorithm. Okay, so in particular, the algorithm cannot just store the entire input. Okay, and its final goal is to compute some function. With slightly more detail, and this is going to be an important definition, what usually people want from streaming algorithms is what's called a tracking algorithm. So we do not want the output just to be at the end of the stream. We actually want to track the value of the function along the stream. So we have some function f, we're going to have some error parameter epsilon, okay? And we're going to have some stream. And what we're going to require is that for any point in time t, so for any timestamp, the output, which I denoted here by r in time t, okay, with high probability over the randomness of the streaming algorithm. So the output is going to be epsilon close to the real value of the function f when it's applied to the stream at time t. So xt is just the stream at time t, so just x1 up to xt. Okay, so I just want to really track the value of the function. Okay, so I'm not giving one output, I'm actually giving many, many outputs. Any questions? Okay. So almost the entire, after decades of research on streaming algorithms, almost all of them are what's called analyzed in a classical setting or a non-adaptive setting. So they have an underlying assumption that the data is fixed before the algorithm starts. Okay, and I'm going to explain exactly what I mean by this. Okay, but in particular, they assume that future elements of the stream, so future data, does not depend on previous outputs of the streaming algorithm. And this might not be realistic in many different scenarios. So just a few examples. Think of a network device, okay, some router, okay, or even a switch. I learned today that even switches run streaming algorithms, okay? These network devices are gonna act according to the output of the streaming algorithm. And once they act, they affect reality. They're gonna affect the network, okay? So the future packets that they see are a function of what they decide, okay? So this, the data is fixed assumption doesn't hold here. Another example, think of an online store. So an online store might be counting, the number of clicks, it's taking the click stream or the view stream, okay, and just analyzing the number of views that every product gets, and it wants to advertise the most, the most viewed product, okay? So here by design, it's affecting the stream of clicks by design. It wants to advertise this product and affects where people click. Okay, and this is going to be a function of previous views and clicks that it saw. And one final and more adversarial example. So think of the area of high frequency trading. So this is an area where people put these servers very, very close to the central stock market, and they're performing trades, okay? So buying and selling stocks, but at an extremely fast pace. So they're doing like thousands of commands in a second. So almost by this definition, any algorithm that they're running is a streaming algorithm, okay? They don't even have time to store things in memory. And of course, once you do a command, this goes back to the stock market and everybody can see this, okay? This becomes public information. And what a malicious company can do, it can observe the buy and sell commands by another company, and then it can perform a small number of, of buy and sell commands just in the purpose of fooling this algorithm and making this company lose money, okay? And this is because the streaming algorithm run by this company is only promised to work in a classical setting. But here the stream is generated in an adversarial setting. Okay, so let me define this slightly more precisely. So we have the two models. The first one is the static, the classical setting, okay? Here the analysis is worst case. Okay, it's not a average case analysis, but they assume the stream is fixed in advance. This means the following. For any stream, so it's really a worst case argument, it's for any stream in the world with high probability over the randomness of the algorithm, okay, the output is going to be correct or within an epsilon, okay? So correct is also like within an epsilon factor of the correct answer. Okay, so the stream is first fixed, and then we're saying that with high probability, let's say with 99%, everything is going to be correct. What happens in the adversarial setting? Okay, so what is an adversarial stream or adaptive stream? So the way the stream is created depends on the algorithm's output. So it's modeled by a two-player game. We have the adversary here. We have the streaming algorithm here. Okay, so the adversary starts, he sends x1. This is the first element in the stream. The streaming algorithm does its analysis and, gives some output back. This is my first value, okay? This is my approximation of the function f, it's R1. This R1 goes to the adversary. The adversary can now think adaptively, and as a function of R1, it can send x2. The streaming algorithm does the analysis, sends R2, and this goes back to the adversary. Again, now the adversary can run some function as a function of R1 and R2 and send x3 and so on. Okay, so this is going to be the adaptive setting. So the adversary's objective is to fool the streaming algorithm at some point in time t. So the adversary is trying to make the streaming algorithm make a mistake, a larger than epsilon mistake, okay? Usually like completely very far from the function at some time step t.
Can you give an example for functions so it's more concrete?
Yes, exactly. After this slide, I'll have an example. Okay. We're gonna exactly see like what the adversary can do and yeah. But maybe okay, just in a second, yeah. So the adversary has unbounded computational power. Okay, so I'm not assuming anything about the adversary. The adversary knows the entire history of outputs, okay, and also the entire stream, okay. What the adversary doesn't know is the internal state or the internal randomness of the streaming algorithm, okay. He cannot see the memory of the streaming algorithm. He can only see what goes outside to the world, okay, the outputs of the streaming algorithm, okay. And he might try to learn it. He can try to learn your internal state by observing these outputs. Okay, the adversary also doesn't know future randomness. So if the streaming algorithm at some point in time decides to flip more coins, the adversary cannot know these coins in advance.
But Eylon, unlike
Yeah.
what happens in game theory, you also assume that the adversary has unbounded resources, right? For example, in the stock exchange, he can buy and sell, doesn't matter to him, right?
Yeah, okay, sure. So I'm defining a very, very strong model. So my adversary has a lot of power. He completely controls the stream, and he has unbounded computational resources and money to buy stocks. And I'm doing this because I'm gonna finally, at the end, show positive results, and it's gonna make our positive results much stronger. However, for most attacks, if you look at the standard streaming algorithms, actually the attacks are very simple, and really with a very small number of inputs, you can completely fool the streaming algorithm, and also very efficiently, and with small memory. Okay, we'll see an example now. Okay. So just before the example, do we have streaming algorithms that are robust, okay, against adversarial streams? And my main message is that if you go to the store and try to buy one, then the shelves are quite empty. So what we do have is deterministic algorithms. If your streaming algorithm was deterministic, then really the two definitions are equivalent, okay? However, for streaming problems, for most interesting, for like vast majority of problems, we have unconditional lower bounds, showing that you have to use randomness. Moreover, in a result by Hart and Woodruff, okay, this is 2013, they showed that what's called linear sketches, and this is a very popular method to build streaming algorithms. So these methods are inherently non-robust. Okay, so all the streaming algorithms using this method are actually non-robust, and we have no hope in using this. So we need robust streaming algorithms. Okay, and now we'll see the examples that you all want to see. So let's think of a very simple example, distinct elements. Okay, so here the goal is to count or approximate the number of distinct elements in the stream. This is also known as the F0, the zeroth moment of the stream. This is a classical problem in streaming algorithm, and it also has a lot of applications, databases, routers, and so on. So let's see an example of how I would solve this classically, okay? I would choose what's called a pairwise hash function, okay? But some simple hash function. From n, so my domain is going to be elements between 1 of n, okay? So my stream is just numbers between 1 of n. And I'm going to choose a hash function from n to some number m, which is large enough, okay? This has to be large enough just to promise me that I'm not going to see a collision with high probability, okay? So something like n squared. And then I'm going to maintain the smallest hash value in the stream, okay? So for every element xi, I'm going to compute the hash value of xi, and just I'm going to maintain the smallest one that I see. I call this v, okay? And so this is very small memory, just storing one element, okay? Storing the hash function and storing the smallest element. And let me already observe something about v. V doesn't care about how many times an element appeared in the stream. So if the element 7 appeared in the stream, it has a chance of updating the minimum value. But if it appeared 1,000,000 times, this has no effect, okay? Only the first instance of this element had a chance to affect V, and that's it. So it only depends on if this element appeared or not, or did not appear in the stream. So V is completely correlated with the number of distinct elements in the stream. And then if you output M over V, you can actually see that this is going to be a good approximation of the number of distinct elements. Okay, so if I had a lot of distinct elements, then I expect this V to be very small. Okay, I have a good chance of one element to be mapped to a random locations, and then one random location has a good chance to be very small. If I have only like 3 distinct elements, then the minimum of 3 random values is going to be roughly near the center. Okay. What happens when I have an adaptive adversary? If I have an adaptive adversary, and this adversary is learning the your estimation of the number of distinct elements at every timestamp. Okay, so he's learning this value. He's actually learning V. What he can do, he can learn the function H. Okay, so this depends on what hash function you chose, but in most cases, he can learn the function H. Once he learned the function H, he can either send a collision. If he sends collisions, this causes the algorithm to undercount. Okay, so we can send a million distinct elements that all hash to the same value. Okay, so our algorithm is going to think of them as one value. And he can also just, with one, and Nati, this goes to your question, okay, just by observing the stream, he can learn the function H. And then just by a single adaptive query, he can send the inverse of 1. And if he sends the inverse of 1, this is going to cause the algorithm to completely overcount. Okay, and the algorithm is going to return the maximum values of elements in the string. Are there any questions about this?
Okay, just a quick question.
Yeah.
So you're assuming the adversary knows about the structure of the algorithm, right? I mean, they don't not only have access to the stream, but also know exactly what's going on under the hood.
I am assuming that, yeah, like if your algorithm is part of the secret, then I'm just considering it as like a meta algorithm with another secret inside. So I'm assuming the adversary knows your algorithm. He doesn't know the internal randomness that you chose. That's the main thing he doesn't know. Yeah. Okay. So let me also say that for this problem, we have no known adversarially robust streaming algorithms. So none of the algorithms works for this model, and actually we don't know how to get adversarially robust algorithms up to our work that I'll show you now. Let me give another example. This is a slightly more practical example. It's in a slightly different context of data structures, but it's exactly the same issue of doing adaptive queries and learning the hash function. So these two researchers in a conference in Germany showed that they can take a web server that implements a hash table, and instead of making the hash table work in time of 1, okay, which is what we expect because we're going to expect to have very few collisions, once they learn the hash function, they're sending all the elements that collide and making one long chain, and every operation of the server is going to work in time of n. Okay, and this is a live demonstration where they really show it. And what they do, they attack a few known web servers. So one is Tomcat. This is implemented in Java. And they showed with like 1 gigabit of internet connection, okay, which is less than what I have now for my laptop, they can keep 100,000 i7 cores busy. So this is like a full server farm. They also did the same for Microsoft ASP.NET and Python and many other examples. I only brought 3 here. And so these were issues that they had to disclose to these companies, and the companies actually fixed them by really choosing new randomness each time and preventing learning attacks. Okay. One other example, which is quite different from the examples I gave so far, this is about a particular subclass of streaming algorithms called sampling. So many streaming algorithms perform in the following way. They simply maintain a random sample of the stream S, okay? So they do this in a very simple way. They just, every element xi that they see, they sample with some very small probability p. Okay, and this is how they have some sample S of the data. And then to approximate the value of the function, they simply compute it on the sample. Okay, and we know this is like one of the most basic techniques in computer science, you know, that sampling is a good idea. You sample your data and it's gonna be a good representation of the entire, the sample is gonna be a good representation of the entire data. And we use Chernoff, we use other things to claim this. And my main point here is that this works only for static streams. Okay, and I'm gonna give you an example of an adaptive adversary that can bias your sample. So I'm going to give a very simple example here, only on 3 elements, okay? But this can be easily generalized to more elements. So think of a stream of 3 elements, 3 numbers, and think of a streaming algorithm that picks one at random. The probability that it's going to pick the smallest number among the 3 is 1/3, okay? That's a very simple claim. What happens when I have an adaptive adversary? So the adaptive adversary starts, let's say, by sending the number 10. Okay, then the streaming algorithm doesn't sample this number. This information affects the output of the stream and thus goes to the adversary. So the adversary sees that you didn't sample 10 and then sends the number 5. Let's say you sampled 5, then the adversary is going to go right and give you 7. And let's say you didn't sample 7. So our sampled element is the smallest among the 3. Okay, and this wasn't by chance. Let's do something else. So again, he sends 10, but this time you did sample 10. So now the adversary is going to go to the right-hand side and send 15. And if you didn't sample 15, he's going to send 12, and so on. So again, the sampled element is the smallest one of the 3. So an adaptive adversary can make you sample the smallest element with probability 1. Okay, so all of the algorithms that are based on sampling are prone to this kind of attacks. And actually, in this work, we show something positive, that if you do want to maintain an unbiased sample, you just have to increase P. And it's very nice to see exactly the connection between the sample size and the correctness with static versus adaptive. If I have time at the end, I'll explain more. Okay, so what are our contributions? We have several different ways to compile a standard algorithm, a standard streaming algorithm, okay, that is secure in the static setting, to one that is robust, okay, one that works even in this adversarial setting. And our compiler uses a small space overhead, okay, and small here is in quotes, because it's going to be small in some cases, and it's not going to be small always, and I'm going to explain exactly when it's small. So we have several different ways. I'm going to just focus on one of them, which we call sketch switching. This is a joint work with Omri Ben Eliezer, Rajesh Jairam, and David Woodruff, and it goes as follows. So in order to exactly tell you what we do, I just need one key definition, okay? And this is not just a definition, it is actually the main insight in our work. So we're defining something that's called the flip number. It's not exactly a new definition, but it's more or less, the key observation is that saying that this is important in streaming. So an epsilon flip number, okay, we call it lambda, of a function f, is the maximum number of times the value of the function can change by a large factor of 1 plus epsilon along the stream. This is very informal, okay? I'll give an example. Let me do something slightly more precise, okay? So the flip number is going to be k if there exist k points in time, such that if you look at the value of the function at these points, okay, they're all very far away by a factor of more than 1 plus epsilon. Okay. So let me give a simple example. So think of distinct elements. Okay, we had distinct elements over a domain of size n. The function starts at 0. Like I start at the beginning, have no distinct elements, and no matter what the stream is, the maximum value of this function is n, just because the domain is of size n. Okay, and the function is also monotone. Okay, and this is important. The function is monotone, so it's increasing in some monotone way between 0 and n. So the number of times it can be far away by a factor of 1 plus epsilon is exactly log to the base of 1 plus epsilon. Okay, which is this number. Okay, and in general, for monotone functions, it's usually easier to bound the flip number. If the function wasn't monotone, then maybe I don't have any bound on the flip number. Okay, so now I can more precisely say what the result is. So we take a standard algorithm, okay, that epsilon tracks a function f. We compile it to a robust algorithm, And if the standard algorithm had space S, our compiled algorithm is going to have space the flip number of the function f times S. Okay, so we get something meaningful only when we can bound the flip number. Okay, by something non-trivial. Okay, the flip number is always bounded by the length of the string, but that could be huge. Okay, and as a result of this compiler, we get the first adversarially robust streaming algorithm for distinct elements. The memory for our algorithm is exactly this, which is the flip number times 1/epsilon² plus log n. This is the best you could hope for statically. This is a tight lower bound and upper bound in the static case for distinct elements. So really up to these log n factors, we're just 1/epsilon factor away of the best possible in the static case. Just a few comments. I don't know of better ways to get this result for distinct elements without going through our compiler. So our compiler is general, but even if you only focus on this particular problem of the distinct elements, this is the best that we know. The log n factor can be improved to log 1/epsilon. So you can use the compiler, but then for particular problems, you can work harder before applying the compiler and actually getting better results. I might have some time to talk about this. It's actually quite interesting. And if you use cryptography and assume that the adversary is computationally bounded, we can actually get the optimal result. Okay, so sketch switching.
Sorry, what do you mean by optimal results?
Yeah, so 1/epsilon² is the best you can do in the classical setting. There's a tight lower bound and upper bound. So because we get 1/epsilon², then this is the best. Okay. And
no, I don't understand. So if you use cryptographic assumptions, then there is no overhead at all?
There is some overhead, but it's like in the log terms.
Thanks.
Okay. Maybe already I could say in a follow-up work, actually, they got a tight result for this particular problem of distinct elements without using cryptography. Okay, and maybe I'll have some time to talk about this. So the high-level idea is the following. We're gonna keep flip number many copies of a classical sketch, okay? A classical sketch meaning a classical streaming algorithm, okay? So we're just gonna have k independent copies. We're gonna carefully reveal information about these copies. And as soon as too much information is revealed, we're gonna take a sketch and just throw it away. Okay, so this is the high-level idea. And now in slightly more detail. So we're gonna keep k, which is the flip number independent sketches. Let's call them S1 to Sk. Okay, and when I mean independent sketches, I'm meaning that we're gonna use k copies of the memory, and every element in the stream is gonna be fed to each one of these sketches. Okay, so they're all gonna see the entire stream. Okay, now let's initialize just I to be 1 and our first output, just let's say it's 0 or 1 or whatever. Okay, at time 0. And then at time t, we're gonna do the following. We're gonna look at the estimate of Si. Okay, so initially I equals 1. So we're looking at the estimate of the first sketch. Okay, we're gonna ask this Si, tell me what is your estimation? Okay, how many distinct elements are there? He's gonna give me some number. Okay, I'm not going to give this number to the adversary. It's very dangerous. This number might contain a lot of information about the randomness. Okay, so I'm not going to give this number to the adversary. I'm going to look at the result I gave last time to the adversary. Okay, so last time I gave RT minus 1. And I'm going to see if the current estimation is very far from the last output. Okay. If they're close, if I had 1,000,000 distinct elements and now I have 1,000,001 distinct elements, I'm just gonna set my output to be RT minus 1. So I'm gonna keep outputting 1,000,000, 1,000,000, 1,000,000. Okay, I'm not gonna change my output to the adversary. And this is fine because I'm allowed an epsilon approximation. Okay, so I'm not giving a mistake answer. Once my estimate is far away, okay, then I cannot just give the previous answer. It might be a mistake, okay? So at this point of time, I'm gonna change my output to be the estimate that SI gives me. This gives a lot of information to the adversary, okay? Maybe even without assuming anything, maybe RT contains the entire, randomness of SI, okay? But at this point, I'm updating I to I plus 1, and I'm never going back to use SI. Okay, and the proof is actually shows that if you have an adaptive adversary, okay, that can somehow fool this entire scheme, then from this adversary, you can show that there exists a classical stream that is gonna fool one of these copies. And you can do this because you can simulate in your head all these previous answers. So you can simulate this up to the time that he does the attack. Okay. So this is really like the high level idea of the algorithm. So let me say, we use this to solve various different problems of streaming. So for distinct elements, it's simply applying the compiler. For many other problems, you have to work hard in order to see what function you want to apply the compiler on. I gave this table here to just compare, just to see the cost of, so this is the cost of the best known in the non-adversarial, in the static setting, okay? And this is the cost we got after our compiler. Let me say something very important. All of these results are in what called the insertion-only model. So this is a model where all these functions are always monotone, okay? And once they're monotone, I can bound the flip number, and this is why we get this result, okay? If you consider the more general case, not the insertion only, but when you allow deletions, okay? And then the function is not monotone, the flip number is not bounded, and we have no results at all. We have no upper bounds and no lower bounds. And for all these problems, we get the first adversarial robust algorithm.
What's a good example of a non-monotone problem that you'd like to solve?
Yeah, so almost all of the problems, the general case, so in streaming algorithms, we use usually what's called the turnstile model, where the elements in the stream are updates to some global vector. So every element in the stream looks like I, comma delta. Okay, and then this tells you to update the ith coordinate of this vector with delta. So the insertion only model means that delta is always positive, but in the general model, delta could be negative. So for all these problems, the general the case is the functions are not monotone.
But is there something nice like element distinctness, that a simple nice thing that's non-monotone that we can?
Yeah, so if you want to estimate, the FP, the pth norm of this vector, and even for distinct elements, okay, just think of, for each element, I can have a sign, a plus or minus sign, okay? And you want the number of distinct elements, but after elements canceled out. Okay, so if I have a plus A and minus A, then this element didn't appear.
Thanks.
Okay. Okay, so I mentioned we have some other results, the sampling that we talked about. I showed you the negative example, but there's actually positive examples and a nice connection between the VC dimension that works in the classical setting and how it doesn't work in the adversarial setting. You can also use cryptography. In some cases, this helps. So for example, this helps for distinct elements, but really the reason is that for distinct elements, we don't care about the names of the elements. We only care about the number of distinct elements. But for example, if you want to compute the median, then renaming elements is a very bad idea. And we have another method called computational path. This method doesn't use k copies, but only 1 copy, so it has advantages in some cases, but still it gets roughly the same memory. The main advantage is the running time. Okay, there's several follow-up works. One very nice work did what actually I think we tried to do in the beginning. So they use the same definition of flip number, and they use the same overall structure, but instead of preventing giving a lot of information by rounding the result to the previous result, what they did, they added noise. Okay, and then they showed using differential privacy that they can protect the randomness of the internal sketches, and they got something slightly better. They got square root the flip number, okay, where we got something linear in the flip number. There's a follow-up by Woodruff and his student showing that they took the same compiler, but they show that you can start with a weaker version of the static algorithm. Okay, so actually you have weaker requirements for the classical sketches, and then when they applied our compiler, they got optimal results for distinct elements. Okay, by solving the classical problem of distinct elements with a much weaker guarantee. And there's been also a follow-up work, but just in a different context of data structures. And let me finish with some open problems. So the first obvious open problems is what happens when the flip number is not bounded. Okay, so when the flip number is not bounded, we know nothing. Okay, we have no positive results. A second, like more fundamental, even open problems, I have no idea how to distinguish between these two complexity classes. So I have no example of a problem which is easy for classical streams, but hard for adversarial streams. Okay, so it's easy to create lower bounds for classical streams. Okay, so the hard part comes from lower bounds for interesting problems. But if I just want a contrived function, it's easy to just come up with a weird function where you can prove that you have to use a lot of memory, okay, to solve in a streaming setting. But here we want a problem, even contrived, which is hard for robust streams, but is still easy in the classical case. And it's very hard to define a problem that goes exactly on this line. Or maybe such a problem doesn't exist. Another thing is better running time. So not only that we pay k the flip number in terms of the memory, you also need to update each and every copy. In some cases, actually, we show that it's you can update k copies much faster than updating each one at a time. Okay, so depending what the underlying problem does, but running time is also a big issue. And also using heavier crypto. So our results use eventually no crypto at all. But even if I assume collision-resistant hash functions, obfuscation, or whatever assumption you want, I do not know how to use heavy crypto. And I assume there should be some connection because we have an adversary that is trying to learn something, and he has errors, okay? And usually this task of solving many equations and learning something, when you see examples that have errors, is very hard. But still, I do not know how to connect this to particular crypto. Okay, so again, this is me. This is my cryptographic view of an algorithmic world. There's so much other examples to be studied here, and I thank you for your time.
Thank you. So there's one question in the chat. If the stream is allowed to have deletions, then clearly the flip number is unbounded. Is that right?
Yes, I guess that was, yeah. So the completely unbounded, and we know nothing about this case. So let me say something. So if you know that there's not going to be too many deletions, then you can actually bound the flip number. And maybe another comment. So think of examples like an online store where you have dependencies of the stream, but they're not adversarial, okay? So you might just have in your analysis some dependency which is not adversarial. Then even though the flip number might be very high in general, you might be able to show that in your case, the flip number is not going to be too high. So you have like a smooth transaction between like an adversarial stream and like a slightly dependent stream.
Okay, thank you. Are there any more questions from the audience?
So do you suspect that really the two models are equivalent?
That's a great question. I think I changed my like belief. I don't want to commit, and this is this recorded? I don't know. This is recorded, so I'm trying not to commit. Still, my guess would be that there should be a lower bound. It seems like quite crazy to believe that we could solve anything we can solve classically, we could solve adversarially. Yeah, but yeah, please delete this part from the recording once we find that my answer is wrong.
Okay. Okay, so I think we can thank Eylon again. Thank you.
Thank you, guys.
Thank you.
Thank you so much.
Thank you very much.
Thank you. Yeah. See everyone in the next talk. Bye-bye.
Bye-bye.